Hello everyone, I'm Cai from University of Tokyo. I'm here to present about our paper, Automatic Texture Compression for Facial Blend Shapes. Recently, the demand has significantly increased for realistic digital human models in various applications such as cinema, interactive entertainment, and the metaverse. But it has been difficult to represent details such as wrinkles and dimples that are dynamically changed with various expressions. Wrinkles are represented by dynamic textures. Here is a blend shape model. With the expression changing, the texture changed to provide fine details to the model. Let me first introduce briefly about blend shape. Blend shapes are a technique used in 3D computer graphics to create facial expressions and other complex animation in the 3D model. The technique involves creating a set of predefined facial expressions or poses called blend shapes, which can be mixed together to create a wide range of unique facial expressions. There are two kinds of blend shape, absolute blend shape and delta blend shape. Here we show the blending of two blend shapes. Absolute blend shape interpolates the position of vertex directly. It restricts the sum of all the ways to add up to 1, which is not convenient to represent many expressions. For example, the mouth open can interfere with the eye close. We cannot make the eye close and the mouth open at the same time. So a common way to do is to blending in a different space, which can leverage the problem. Here we add the position difference to the neutral face. Now we can close the eye and open the mouth together. In this way, we can also blend the textures for the new expression V beta to make a mesh with dynamic textures. To deal with the dynamically changing textures, we need all the corresponding textures of the blend shape. But since texture data is significantly larger than the vertex coordinate of the meshes, storing the raw texture for all blend shape meshes is impractical, especially for real-time applications. So our motivation is to find a method to store all the high-res textures in a much more efficient way while preserving all the details. They can be easily implemented in modern game engine for real-time purpose. In our final paper, we store all the textures into only one neutral texture and 4 different textures. Then I'll introduce some related works on facial detail representation. One kind of the method is using geometry to represent the facial detail. These approaches have extremely high computational complexity and are unsuitable for real-time applications. Recently, neural network is popular in generating facial textures. Some work also use neural rendering directly to represent facial details. Although neural networks can generate high-quality textures without storing all the corresponding textures, they are very expensive to generate the textures and need great amount of training data. Our approach. Let us assume that we have n number of RGB textures. Our algorithm computes one neutral texture and 4 RGB difference textures. And then, every original texture can be represented by a small weight map with 4 channels. As this image illustrates, every original texture is reconstructed by adding the corresponding part in the 4 different textures with the weight map. Note that we have 4 source textures because the weight maps can be efficiently stored in RGBA texture space. The weight W is smoothly defined, such that it can be stored in a downsampled image without significant loss of quality. In this paper, the ratio of downsampling is 8, thus the size of the weight map is 64 times smaller than the original one. Our approach includes these main steps. The procedures are done in the different textures. We divide all the different textures into pieces. Next, in every subspace of pieces, we cluster them into 4 cluster centers to represent that subspace. We then can stitch them into 4 different textures to form the final 4 textures. Finally, every original texture can be reconstructed by the generated different textures. The deformation of the entire face has rich varieties, but if we focus on a specific location, the deformation can be approximated with several modes. For example, a forehead exhibits horizontal furrows when the character raises the eyebrows and vertical furrows when the character frowns. To take advantage of such a locality, we first divide the input texture into small fragments. However, we do not want to have obvious boundary between the subspaces that can cause seams in the final result. we compute each subspace as smooth mask produced by the biharmonic weights. We show one of the subspace masks in this figure. We can see it is smooth and localized. Here we can see in one of the subspace, we extract the corresponding location for every original textures. Then in every subspace, we have the corresponding fragments of the original textures. We extract the dominant modes in each subspace using k-means clustering method, where the number of the clustering is 4. Every original textures in the subspace can then be represented by its nearest clustering center. We now have 4 fragments for every mask. We are stitching these fragments back to 4 full textures. Naively adding up the fragments with the same texture index will lead to the blurring of the texture around the border of the fragments. Hence, we optimize the combination of the fragments for each texture such that the adjacent fragments match together. Our subspaces are actually smoothly overlapping with each other. In order to reduce the error in the edge of each subspace, we define the cost function based on the difference in the overlapping area when stitching back, and then we optimize the arrangement based on the cost. Using the optimal arrangement, we can get the 4 different textures in the end. We now get the 4 different textures, and for each original texture, we know in each subspace which clustering center it belongs to. We simply extract the corresponding clustering center from the different texture and add them together to get the reconstructed result. Now, we compress the original texture into only 5 textures with corresponding small weight maps. We show the result of our algorithm. To evaluate our texture compression performance, we compare root mean square error with the PCA, which is often used in the texture compression of Blendshapes. As the ablation study, we also perform the comparison against the compression without permutation optimization. We observe that our approach without permutation is generally better than the naive approach of PCA. Our approach with the weight maps and the permutation optimization constantly produce the smallest error against the other approaches. We choose one example to illustrate the detailed difference. The error of PCA is very large in areas such as eyebrows and lips, where there are a lot of fine details. Our work can preserve them better. We can see the weight maps change according to the Blendshape weights. The dynamic textures follow the weight map. But we think it is not enough. We extend our texture compression for Blendshape to the Blendshape in example-based facial rigging. Production typically uses the measures of fax poses to create the Blendshapes for the facial animations. As facts are typically made up of 50 to over 100 independent meshes, there is a demand to build all fax Blendshape meshes from the limited number of captures. Example-based facial rigging presents a retargeting technique to synthesize Blendshape meshes of fax poses from a small number of expression capture. However, this work focused on the facial geometry, not the texture. The basic idea of example-based facial rigging is to optimize the generated Blendshape mesh V* such that the training mesh Vn can be reconstructed as the Blendshape of generated meshes. The generated meshes can be compatible with common Blendshape application like ARKit. We synthesize the texture for generated Blendshape such that it will reproduce the original compressed texture for the training meshes. This can be done by choosing the weight map for generated Blendshape using a similar equation. Unfortunately, the equation alone cannot specify the weight, since the equations are underdetermined. Hence, we calculate the weight maps in the constraint that the weight should be as small as possible as a regularizer. In that constraint, we can get the weights for the generated meshes by the example-based facial rigging. Here, the B matrix is the pseudo-inverse of beta. We show the real-time ARKit track result with iPhone. Conclusion. To conclude, our method provides a fully automatic and real-time texture compression for facial Blendshapes, with extension to support texture generation for example-based facial rigging. Currently, our work only compresses the orbital texture. ignoring all the other textures such as normal maps, specular maps, and roughness maps. Also, extending our compression method to other textures is straightforward. There is potential to further compress the set of textures by leveraging the correlation between them. We are also interested in applying our methods other than facial textures. Especially, we are interested in efficiently representing the wrinkles of the garment in the texture space. Thank you very much. If you have any question, feel free to ask me.